Herkese merhaba tekrar. Beşinci oturumumuzda bugünkü Epic Games teknik evanjelisti Joseph Azzam bizlerle birlikte olacak. Unreal Engine Niagara'nın gücü ve çok yönlülüğünü kullanarak canlı olarak devasa kalabalıklar oluşturmak ve milyonlarca birimi simüle etmek hakkında workshop yapacak bize. Şimdi kendisini davet ediyorum.
Hi.
Hi. Hello, Joseph. Welcome.
Thank you. What's up?
I'm fine. How are you?
I'm good.
Hope you're staying safe.
Yes, I am. Yeah, so this is the second edition of Indieway. Nice.
Yeah, it's really nice to see you again. You can start whenever you are ready.
All
I'll
right.
be here.
So,
I'll help you with the questions at the end.
perfect. So this is a presentation that I actually gave a bit before, so you can find a shorter version online. Today I'm going to give a longer version where I'm going to go over details. If anyone at any point has any questions, because from the comments from the previous talk, I noticed that a lot of people have some question about it, feel free to send them in the chat and I'll try to cover them as I'm giving the presentation. If not, you can always just ask me at the end of the presentation as well. Yeah. Okay, cool. So I'm gonna start sharing my screen. Yeah, so the presentation is simulating large crowds in Niagara. This is my Twitter handler. If you also missed this presentation, you didn't watch it live and you still have questions, you can always just tweet at me and I'll try to reply to them there. So I'm just going to show you a video of what to expect. And this is basically a render of the end result. And this is basically we're using particle effects here, in this case, to replace basic AIs by smart particles. And this enables you to just fill the scene with an absurd amount of number of AIs. In this case, it's actually 1 million AI on screen. And they're not static. They can actually move and interact. There's a lot of functionality we can add. And in this presentation, I will cover them in details. All right. So let's talk a bit of AI. But first, I would like to mention the asset that I mentioned. To create my scene, I use some of the Quixel Megascan assets. From the marketplace, the Unreal Engine marketplace, I got the Sci-Fi Town 2 Vine Branch and the Crow Protofactor Inc. for the birds. And I would like to thank the Niagara team for helping me answer my questions, getting me familiar with the tool. And I would like to also thank Hassan Murad for his help as well. Okay, so I first want to show you that the problem we usually face when using games. So let's go over the traditional technique of having a lot of AIs on screen. And usually what we're going to use traditional skeletal meshes, and let's see how quickly we can hit the limit. So for this experiment, I just have a simple box that is simulating physics. And then I have a blueprint that is just spawning AIs. And this blueprint right now, it spawns, let me show you the behavior of those AIs, it's very basic. It just asks them, go and follow this box. It's a simple move to the actor. And basically what I'm going to tell it, hey, spawn 20 by 20 AIs. So this is basically 400 AIs. And if I show the frame rate, right now the frame rate is at 70, 80, 90, something. If I hit Alt play, okay, this is actually, let me reduce the number. Let's start basic with 100 AI. That's how usually in games you have. And right now you're having around 34 FPS. By the way, just to give you some background, right now I'm running on my laptop this presentation. So it also depends on your computer speed. Okay, and right now the performance is okay-ish for this number of AIs. But we quickly can hit this limit by, let's say, I don't know, we want to go by 30 by 30. So that's around 900 AI, that's around 1,000. And right now the performance is running at 10 FPS on the laptop. So before starting to optimize, you want to understand more your bottleneck. What is actually causing this performance issue? And stat FPS is not really helpful, it just shows you the frame rate. What you really want to know is, okay, just give me a moment. I'm using a new keyboard and I need to find a button that is not available on this keyboard. So usually I use the tilde key to open the console command on my keyboard. I can't find this button right now on this keyboard, so let's just pretend that I did. And we will use the command called stat unit. So I'm going to type it out in the search bar instead. And stat unit will show you actually how much performance is being used by the game thread and how much performance is being used by the render thread. I actually have some pre-recorded footage so I can show you an example, and this is how it will look like. So it basically shows you the performance. Is it bound by the GPU or by the CPU? So by running it on this experiment with the 900 AIs here, we can see that actually it would be bound by the graphic card, but also by the CPU, actually. So to get a better understanding, what you need to do is fire Unreal Insight. If you don't know what Unreal Insight is, it's a new tool that's going to replace our debugging tools, which unify everything in one place. And you can find it inside of the directory of Unreal Engine. So if we write Unreal Insights.exe, it usually comes with the engine in the same folder. You have to launch it. And then you want to open your project. So they're not running at this, it has to run before you launch your project. And once you run it, it will start debugging the scene. And in this case, what it's going to give us is this. So I already have a screenshot of this, and this is a breakdown of a single frame. So it's telling us that this is our GPU frame. You have the game thread, you have the render thread. And it shows, okay, well, Tick is actually using a lot of the performance. If you go deep inside, it can show you, okay, now you have some physics interaction, you have some animation update for the bone position. This is basically what's sticking the most, and that's what's using some of the performance. And basically, in order to do so, to disable them, what I created this blueprint. The same blueprint that we're using for Spawn, I'm just accessing all the skeletal mesh information and I'm disabling some settings. So what if we turn off animations? We used to be running around like 10 frames per second, the game. If I turn off the animation, we just gain around double that performance. But if we look at the AIs, they're not actually animating at all. They're just moving. Well, that's because our bottleneck was the GPU, but also it was the CPU. So another thing we can disable is the movement component itself. And disable the movement component. 1 second. Gonna open this blueprint, the one that is spawning them. And this is where I'm actually accessing the AI properties. So this is how we're basically changing the animation and updating the mesh properties, etc. So we have a spawn AI, we are casting it to character, and we just want to do disable movement. Now that we're disabling the movement, hit compile, save, hit play again. Our performance is actually went all the way back to 35 frames. And okay, well, great. I mean, we have performance, but we have AIs that are neither moving or animating, and that could be an issue for us. So if we look into the Unreal Insight, something more specifically that is using the performance is actually physics interactions. So we don't have to completely disable movement. All we have to do is disable physics interaction. So if you look at the property that's called physics interaction, and we disable that instead, and let's just not disable the animation instead. Let's just connect this one here. and disable the physics interaction. Hit compile. Now we will hit play. I mean, the performance dropped again, but we still gain a bit more. But they're not moving the box anymore. And this is because they cannot really interact with the box. And the reason why they can't interact with the box is because we disabled physics interaction. However, now that you kind of understand the bottleneck, you can know how to fix it. And I'm going back to some slides to show you how Bonex works. So first thing first, you want to understand, is it from the render thread? Is it the game thread, or is it draw calls? And to do so, you have to use the profiler, which is in case Unreal Insight. So for polygon count, if that's the performance issue, you can use LODs, and inside of Unreal, they're very easy to generate. So let's just say we have a skeletal mesh in this case here. If I go to our minions, turn off the search, and we get our skeletal meshes here. You can easily generate LODs by just going here and hitting how many LODs you want and hitting the generate button. This will take a couple of seconds, but it will automatically generate low polygons just immediately inside of Unreal. Second, well, the animation skeleton update. In our case, we disabled animation for everything. However, there's a tool inside of Unreal called the Animation Budget Allocator that does that automatically. And it gives priority for meshes, meaning that meshes are in the front can actually have priority, so they can have animation playing at full resolution, while the one in the background, they don't have to update each frame. They can just periodically update. And depending on your computer performance, power, you can actually set this to scale. So anyway, dynamic shadows. Shadows are also something that use some of the performance cost. What you can do is tweak your cascaded shadows, meaning they don't have to be calculated all the way up to 1 kilometer. They can be updated all the way to 20 meters. And then you can also use capsule shadows, which is usually used for mobile. It's a way to create fake shadows, but they're really close enough that are really good. And instead of using the mesh to calculate the shadows, they use the physics capsules, which is less detailed, which gives you like better performance. Now, for the game thread, you want to use pooling. So what is pooling? I have an example for pooling in this case here, and I'm going to show it. So it's called. So we have two AIs that are going to spawn behind this box. We have this shiny pooling one, and we have this one that is not actually pooling. And let's hit play and see what happens. So, 1 second, this is a skeletal mesh. Oh, there's no navigation, sorry. Let me add some navigation here. Build paths. Okay, now when I hit play, we have two AIs that they're running. And once they get there, they're dying. Now they're supposed to be simulating physics, but we kind of disabled that at the moment in the previous example. So in this case, what's happening is each time this AI arrives here and dies, we spawn a new one here. However, in this case, every time he gets here, what we do is we just spawn a mesh in its place and we move the AI back here. So pooling is basically like recycling. You're not destroying and creating a new AI. You're just adding a mesh in its place and moving that AI and resetting it. And if we look at the code, it's quite simple. This is a regular AI. And you just the behavior is like spawn, go to destination. And then once there's a reset function that basically just looks, okay, well, we probably want to change the location back to the original location. And we want to change his health to 100 because when he died it was 0. And we want to reset the function for death so he can die again. That's about it. Well, here it's mostly like, well, he died. So instead we want to spawn a new AI, and that is actually can add a lot of performance to the memory. There's also maybe your code is heavy. So just use async instead of when possible. So you can always spread your functionalities over multiple frames. You don't have to spawn all the AIs on the same frame. You can put some delays in between and spawn them over time. Reduce the tick interval or use a timer. So ticks is usually one of the biggest performance you might notice. By default, it's on in every blueprint. So if you write tick in the console command, you can see all the blueprint that are ticking. To disable tick for things that don't need to be ticking, you can, for example, go here and disable it, or you can go to your project settings and you can disable all ticks in general. So you can make it by default, tick is disabled, and you have to enable it to use it in blueprint. Can blueprint tick by default. Or yeah, just use a timer that is not doing it every frame. If you have too many units, you can cluster units. And for example, if you have thousands of AIs, instead of moving each unit individually, you can group them together. So now you can have, let's say, every 5 AIs are a single entity that is only calculated once. There's only one point being calculated at where they move, and they're all just moving with that point as a group. And you only separate them once there's a need for them to separate. So technically you pay the cost for 1, but they look like 5 units. And of course, there's the movement component cost, just disables the features you don't need. Now for draw calls is sometimes another type of bottleneck you're gonna face, and they're not equal. Just having 1,000 draw calls of small meshes spawning immediately and having 1,000 draw calls of spawning really large heavy meshes with skeletal meshes and bones and animations, they're not the same. So you want to make sure that you can reduce the amount of bones. There's like bones out of these as well. You can use the animation sharing manager to help you also reduce the cost. And also by just reducing the amount of polygons and all of that, you will also save some type of performance. Now, how should you actually optimize AIs? And this is actually quite common for games in general, that everything the player sees in front of him and can interact with them would be running at full resolution. So that would be like you have 3 tiers of AIs. The high AIs, they have complex stuff, complex logic. They can interact with the player. They have animation that is really detailed and accurate. The medium AIs, they're somehow in between. They're slightly lower polygons, slightly less complex animations. They're really basic. They're just like walking around pretending to be doing something. And the low AIs in the distance, they are so far you can barely tell what they're doing. So they can literally be like 10 polygons and doing some repetitive animation that no one knows what it is. And from a distance, it will look great. So this is where you can do a lot of optimization and have those big crowds. Because even if you have thousands of AIs, the player will only be able to interact with how many? 20, if you're lucky. And then everything that is not in the player's view, well, you make them disappear. You would still have some logic to calculate their position possibly, but everything else would be disabled. So now with particle effects, this is where they excel usually at doing low AIs. But with Niagara now, you can do even smarter particle that not only they can do the low AIs, but they can even do even more low AIs, but also they can replace some of the medium AIs. So you can end up with just one giant particle effect, and that is replacing the front-facing AIs, particles with some AIs that the player can interact with. And this is how you can hit large numbers. So I'm gonna start with Niagara, and we're gonna do a very basic example. We're gonna start by going to a map. It's called basic. And we're gonna create a basic effect. So if you have never created an effect in Niagara, we're going to create the most simple one I can think of. I'm going to do it from scratch, but there are templates you can use. So we're going to create a new system that is empty and hit finish. And I'm going to Niagara system basic bird 2, because I already created one. Now, to add an emitter, if you need an empty emitter, you have to go to view options, show developers content, show engine content, and show plugin content. And now we look for an empty emitter. And that's it. Sorry. Yeah, we're gonna take a completely empty emitter. That way it's like completely from scratch. And I would like to disable those folders again once I'm done. Cool. So first thing we want to show is our mesh. So we're going to start basic with a bird. We're going to use a mesh renderer and we want to display this bird. So we're just going to look for a bird or a crow. Here we go. We added the bird. We can't see anything yet. That is normal. We want to spawn. So for spawning here, we want to spawn burst instantaneous. And one second. Okay, found it. This module has unmet dependencies. I'm just going to add this, and it should manually add it for us. Now we have the emitter state, and we want to say that the life cycle is going to be running self, so I'm going to follow the emitter, and we want it to basically run once. So it's not a particle we want to loop. We want it to run just one time infinitely. So now the birds we create are always there. Okay. Compile. One second. Just gonna move it back to the empty one. The completely empty is actually too empty for me. So, yeah. All right, now that we have our mesh renderer, we still don't see it yet. And that's because we have to burst it again. And say we want to spawn one bird. Should have initialized here in this case. And we want to also make sure that the bird doesn't die. So, one moment. Okay. This is where you can pick if it's a CPU or run on a GPU. And later in the presentation, I'll explain which one you should choose in between. We haven't set the bird because I moved it again. So we just add the bird. And now we have a bird here. Great. So we have a bird, but it's actually spawning and dying. So we want to just keep it alive and just don't kill the bird, basically, when the time ends. Now, how can we animate this bird? And first, what we need is some animations. So to explain how to actually control the animation, first I want to show you the material setup we have for this bird. Okay, so you have your regular diffuse and normal map that you have for your bird with the particle color. So this is useful for debugging purposes if I want to change the color of the bird or just adding randomization. I'm attached some roughness, and this is how I'm controlling the animation. So those textures, I generated them using 3D Max, but there are scripts in Houdini or Blender that can do it for you. And it's basically we're converting skeletal mesh animation into a baked animation. So we're using vertex animation. And this is a built-in function inside of Unreal that just plays vertex animation, and you can attach directly to the work position offset. You can find it on our docs. So you just hit Control Alt, you can go to the docs, and it tells you step by step how to actually do this setup. So if you're not familiar with vertex animation, it's one texture that saves the position of each vertex over time. And this is how it is. So to create it, I basically combined multiple animation that I had. So I just went to the bird and it had those animations, and I put them all together inside of an animation composite. So I'm just going to load the animation composite. It's going to take a moment. And you can see all the animation that are set back to back. And then what I did was I hit the record key and I saved them all as a single animation that I exported and baked. Anyway, so now that we have the exported animation and it's connected here, we finally feed one parameter that is which frame to play. So the frame selects which line, which position basically we want those vertex to be. And it's actually fed as a dynamic parameter right from Niagara. So materials and Niagara can communicate very easily between each other. And if we go back to our effect now, we just need a way to actually play it. So to do so, we just need a very simple custom function. And this is where Scratchpad comes in. Scratchpad is our visual scripting language for HLSL inside of Unreal. So if you're already familiar with Blueprint, it's going to be a very easy transition for you. And this enables you to unlock all the power of HLSL so you can do your own functions. Okay, so I'm just going to call it a Scratchpad. Call it Scratch Animation. And this is the interface. I'm going to slightly reduce here so you can easily see on the stream what I'm doing. Actually, I can just take this out and make it full screen. Great. And basically, it just gets parameters and set parameters. And for that, we're going to use a function that's called play animation. This is an animation that I wrote customly, and I'm going to explain. If I double click, this is the function, and I have some slides I can explain it properly. So basically, what we have is 3 properties for each animation. We have the state, which is like an ID. This is how I distinguish which animation I'm playing. So I'm just going to number them. We have the idle, walk, and takeoff. Then you have the start and end frame. And those defines on that texture we created, which line starts and which is the end line for each animation. So basically idle is actually from 0 to 104. And then walk is from 155 to 170. Takeoff is 171 to 209. And then basically what I'm doing is I'm just, over time, I'm incrementing the frame animation. So the animation frame is literally just the start frame, plus how many frames has already elapsed, plus depending on the animation speed, the time and the frame rate of the animation, how much I should increase it, each frame. Okay, so there's also some conditions here. Means if the animation reached the last frame, then it will reset and start back at the start frame. If the animation changes, it will reset the new animation start frame. So just make sure that, oh, okay, now we switch to the next animation. I also want to go back to its original start frame and reset the elapsed frames. And I'm going to ignore that step if it's the initial state. So the initial state is like state 0, what I call it. And it enables you to configure this function. So sometimes you want to add random offsets. So you want to change the elapsed frames, and you don't want it to reset while you switch to the next animation. So this creates some type of randomization in your animations. So yeah, let's go back to our presentation and let's start using it. It's simple. This function has the animation frame that I'm going to connect to the output. the animation elapse frame, and the animation state. And those are properties I want to actually save inside of each particle. So each particle has its own animation frame, elapse frame, and the animation state. So we just have to go to right-click local and change the namespace to particles. This is where the variables will be saved. Okay, now, same thing for the input. Well, we know that the animation elapse frame is actually the one we just created. So we're just gonna connect it here and connect. The animation speed is actually an input. So we're just gonna connect it here. It's an animation speed input. Animation frame rate, it's also an input. The previous state is literally the state we saved. So that is the state. Let's see. The start frame, end frame, and state are actually properties that we want to set. So let's say we want to play the idle animation. If I go to my presentation here, the idle animation is going to be our first state. It's from 0 to 104. So let's do that. It's going to be our first state from 0 to 104. And now we hit apply. And we just go back to our functions. And we call our animation. So let's just say scratch animation. We want to make sure the frame rate is set to 30. And our animation is set to 1. You can also set the default values here by just clicking on one of those frames and saying those variables and saying, for example, our input frame rate is going to have a default value of 30 and the animation speed is going to have a default value of 1. Hit apply. And now it's set as a default. Cool. The bird is still not playing. And the reason is, even though we're doing the calculation, we just need to send the frame to the material itself. So all you have to do is look for dynamic material parameters. And by default, it has state, frame, speed, and emitter age. And the reason why we have those variables named is because it read the material. And if you go to our material, you can see that I already named them inside of the material here as state, frame, speed, and emitter age. So that's really convenient. And all we have to do is just set the frame. So that property we just created that we outputted it into the particle, which is our animation frame, you can just drag and drop it here, hit compile, and wait a moment, make sure animation speed, animation frame rate. Oh, sorry. This is a 0, this is 104, and this is back to state 0. And this is animation 1. Apply. Cool. And now we have a bird that is actually moving. What if we want to have multiple birds? So we can just go to spawn bird instantaneous, and we're just going to say we want 4 birds. The problem with that is they're all spawning on top of each other, so you can't really see it. So instead, we're just going to say a box location, and we're going to randomly spawn them in a box. We don't want to spawn them on the z-axis, so the z-axis will be zeroed out. And now we have 4 birds. We can spread them further if we want, so 200 by 200 grid. Good. But they're still all playing the animation at the same time. And this is where the configuration state comes in hand. So on the particle spawn, we can actually change the elapse frame. And we can change the animation state. So let's just write animation here. So we're going to configure animation state to be the 0 state. And we're going to put the animation frame on top as well. And we want to random, basically this one. So we're going to set a random range float. It's going to be anywhere from 0 to, we have 104 frames. We have 104 frames, and we want to divide them by 30 frames. And now we have each bird is playing an animation differently. So we have this randomization. final step is, what if you want to play multiple animations? And what you can do here in this case is just add a simple if condition, and then you can switch between, one second, here you go. You can switch between different animations just by changing their states on a certain condition. So this was animation 1, and we want it from 0 to 104. And you can also rename those variables for convenience. So I'm just going to call it state. This one's going to be start frame. And this is going to be our end frame. Okay. And our second animation, according to the presentation I had, is actually 155, 170. Here we go. 155, 170. State 2. And we just need a condition here. And the basic one is, well, if we want to transition between idle to walk, we're going to check the velocity. So we can really simply just get the velocity. And if you look for velocity of the particle itself, we're going to get the length. And if that length is bigger than, once again, I need to convert this to a float. And this is a vector. So we want to convert this to a vector. If it's greater than 0, means the velocity is actually, okay, if the condition is true, then it's A. Then in this case, if the velocity is actually equals 0, we want to be playing the idle animation. Hit apply. Finally wait, compile and save. And nothing happens yet, but the easiest thing to do is, let's just set the velocity manually. So if we drag the velocity here, and we put it in the particle spawn, right now our velocity equals 0. What if we wanted them to move? So we just have to say velocity equals 10. And now we can see we transition to the different type of animation we have. If I put it back to 0, they're now idle again. Good. So this is how I did the setup, and this is quite simple. But let's see some examples of the stuff you can do. So start with this basic example here. And if we look at the bird, this is a very similar to the setup we just did, except if you look at the animation state, okay, just one moment. I have to pause for a moment. All right. Yep. Sorry, I had to pause for a split second. Now I'm back. Yeah. So we have the bird here moving. If we look at the animation state, it's actually similar to the one we just created. Well, we have play animation, but we have so many other conditions because we wanted to say like that bird has to take off, has to land, has to run, and this is different conditions that set this. So if you look at this example now, if I press the button and hit activate, we can see it's walking, it's taking off, it's flying, and then it's gliding, and then it's landing, and it's back to idle. Another example, what if we want those birds to basically just place them on a certain type of object. Here we go, just one moment. Because we can have collision and simulations of physics, we can actually easily just put a particle effect and they will actually understand their position on a certain different set of objects here. Another example here, if you want to easily place some birds in your level, you can have a flock of birds. You can have parameters where you can easily tweak. So let's say instead of 50 birds, we want 500. We can even go for 5,000. And we still don't have any performance issues. But if we go for like 50,000, then now we have a frame drop because we had a different bottleneck that I'm going to cover later, even in this presentation, how we can even reduce that one. So now let's bring it back to 50. You can also increase the radius that we want them to cover. So instead of 250, we can say like 400. And now they're covering a bigger area. We can use vector fields to make the animation more random. Like, so now they're all flying all over the place. Depends on the field I have. And this is an interesting one because 2 years ago at Guest, I tried to give a presentation on how to make birds on a tree. And this presentation just evolved into the presentation you're seeing today. So that's cool. And let me show you, if we have birds on the ground, they can go and fly and land on a tree. And the reason is they can land on a tree is because Niagara understands meshes. You can sample a mesh. I even selected the top of the mesh by having a separate material ID on the tree. And then the bird said, okay, give me a random point on those positions where I can land. And they just landed on it. We can actually open this to show you the example. It just have a sample static mesh where we end the static mesh to sample it. And then we do a lerp between the two positions, between the ground position and the tree position. And then we just update the orientation as they go. This is also an interesting one. I mean, this presentation took too long that this guy fell asleep. So I'm gonna wake him up. And to do so, I just have to give here, and then there's play somewhere, editor. Okay, update animation in editor. And once enabled, he starts to walk. And I have to just refresh this. So I'm just gonna go here. And now notice as the player is walking, you can see he's pushing away those birds. So I'm going to do is take this character and I'm gonna hide the mesh itself. And now you can see we have points that are sampling the character itself, the bones. So they are actually sampling the bones here. And that information is being used to tell the birds to move away. If you look at the particle effect, I actually have two. So I have the mesh influencer, which is those points you just saw. And those are for visual purposes only. I can disable the renderer. They will still work fine. They're still moving away. And basically, we're just sampling the mesh. However, there's a different particle effect is the bird itself, like similar to the one we had. There's only one additional module that I've written, and I can show you in a bit. But what's interesting is we can use direct reads, and direct reads can actually read the information of a different particle. So you can have two systems that they know information about each other, and hence you can create more complex effects. Now, basically, this is the function I'm using to move away from the player. And it's quite simple. It's basically looking at, okay, give me the position of the player and give me my position and create a vector based on those two. And then based on the radius to push between them, as the player gets closer to this radius, I want to increase my speed to move away. That's about it. And then we're slowly just changing the location of that bird. Now, those are interesting effects, but how do you debug them? And to debug these, there's a few easy methods. The simple one is just using colors. So if we go into the initial one, the initial bird we started with, and we just use this function, which is basically just changing the color of the particles, and we can link them to some variables. So in this case, I just link them to the animation state. Hit compile, and now we can see the bird is changing colors as he's transitioning between animations. Another way that I use to debug is something that came with Niagara, and is the attribute spreadsheet. So if we go into this bird here, and we can just go into Window, Developer Tools. A second. And look for the attribute spreadsheet. It is one second. Oh, sorry, it's here. Okay, so this is the attribute spreadsheet, and it can actually capture some information. So let's just say that we have an emitter we have to select first. So let's just select the, I don't know, the birds, because we have multiple birds. We hit capture, and it's showing me all the attributes that I need, like orientation, position, everything. I'm going to toggle everything off, and I'm just going to look at the actual position to see them change. So right now, they're not going to change that much because they're in the viewport of Niagara. But how can you actually debug a system inside of the engine itself, like the game? So you can actually go into your level and look for a property called force solo. Once you do that, now you can actually get these birds here. You want to be in simulate mode, so you want to hit simulate in this case. And then in viewport, you can select the effect here. You can hit capture, and now you can see the values of those birds. And after the character actually pushed them, I'm going to hit capture again, so you can see that it's actually changing. It changed for some birds. So this one here over here changed. And the final method is a quite practical one, is to just have some numbers on top. So if we go into this bird here, we just added a sprite renderer on top that I offsetted the value, and the material is really basic. It's just a dynamic parameter that I'm converting to some floats that we can see here. And it's connected to the material. So this, we can connect multiple values. In this case, we're just setting like the lifetime of that particle. And thing is, those particles right now, they have a velocity of 0. I can't really read it because they already landed. Let's just reset the particle. And if we hit activate, we can see those values are changing, but it's super fast for me. So a very useful tool that I used is versatility, and versatility is just an interface where you can extend the functionality of the engine itself. So it just has some time dilation. I'm going to run this versatility here, and I'm just going to change the speed. So what we can do is when I activate here, I want to set the time dilation to 0.1. So it's going to be 10 times as slow. Activate time dilation. Let's say. Oh, need to hit. Okay, see, and now we're seeing in slow motion, and we can just see those values evolve. If I want to set it even slower, now we're watching it in even slower motion. And once you're done, you can always just, okay, go back to the regular speed. Cool. So these are my workflow for debugging. And now let's get more interesting. So now that I covered the basics of how I went over all those techniques to create those effects, I want to show you my final effect where I pushed all of them into a single one. Okay, so if we go here into our maps, this will take slightly a minute to load. Yeah, it's not too long, hopefully. This is a scene where I have 500,000 army fighting another 500,000. So see. I'm gonna close this guy. So the way we have these guys is basically the way I managed to get this type of performance is, remember when we actually had the bird and we hit 50,000, that was a lot. A simple trick, if I zoom in here, you can see that by hitting C on the keyboard, those one have lower amount of polygons, the one in the back, but the one way in the back, they're just billboards. Billboards are just a 2D plane and they're super optimized to run in quantities. So the way I did it was inside of Unreal, I just placed the mesh and I put a camera inside in front of it and rendered it as a video that on a green screen that I later just created textures out of it. So I can actually show you the baked ones. And this create a texture like this guy. So this is all the mask, for example, for reflection. But yeah, these are all the frames that I want to play. They're just looping. And in the back, they don't have to be accurate. They can do anything you want and no one would notice because they're really, really far. And this is even from the top view. If you go to the bottom view, the player can barely see anything. So this is how basically you can just replace the meshes in a distance with some basic billboard that is moving and gain a ton of performance. Another thing you can do, if by going to the particle effect itself, there are some handy settings you can use. So you can enable frustum calling, means anything that is not viewed inside of the camera, it will not be rendered. So this an automatic optimization you can just use. You can also call by distance if you want. Now, once you have those three, how do you switch between them? There's a render visibility tag that you can use. So I labeled this one as 0, and the second one is labeled as 1, and this one was labeled as 2. And then I created a very basic module that is basically, if you look at the code here, just have to go to the original parent. And if you look at the code here, is basically checking the camera position, the particle position, and based on that, it is switching, saying like, okay, if that distance, then I want to switch between the visibility tag to something. And if that distance, I'll switch to something else. Finally, how they're moving is basically each unit is using directory to know the position of the one in front of it. So they're not actually moving as a full, they're not, everyone is calculating their own doing calculation. It's actually, there's only the first line that is deciding where to go, and everyone else would just follow the unit in front of it. So if I hit play actually and I kill one unit, you're gonna see they have some smart logic to just attach to the unit in front of it instead. So there's like some handover that's happening. If the unit in front of me dies, the unit before dying is going to tell me who's the unit in front of her. And that's what's going to happen right now. So let's do this. If we go here and I'm shooting at 1, you can see one unit follows me and the one behind it actually just takes its place. And another thing I added is when I get closer to unit, if they are particles, they will just move away. So I don't have to worry about collision because they will never actually hit me. And if I shoot at one unit, what's happening is I'm replacing the unit that I'm shooting with an AI. And basically that AI becomes something I can interact with. And this is how I can gain performance.
Joseph,
Yeah.
okay, we can hopefully finish now. We are nearly out of time.
Right. So yeah, sorry, the presentation is almost done. I think if anyone has any questions, then I can take them.
There are no questions right now. So thank you a lot for joining again this month. It was nice to meeting you again.
Anytime.
Thanks again for the workshop. Hopefully we see you again. Bye-bye.
Bye.